my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on EDEXCEL topic 19, Modern Analytical Techniques 2. So in this video we're going to be looking at all the information that you need to know for EDEXCEL chemistry. So if you are studying A-level chemistry and it's EDEXCEL, then this video is specifically designed for you. So sometimes you can look at some information or some stuff online, and you can wonder if it's actually in your specification, and if you actually need to use it for the exam. But with this video, everything in here is dedicated towards EDEXCEL, so you know that anything in here is relevant for you. And there's actually a full range of videos for EDEXCEL, ranging from topic 1 all the way up to this one, which is the last one, which is topic 19, on my Allery Chemistry YouTube channel. They're all for free. There's loads there. There's also some whiteboard tutorials, and there's also some exam technique questions as well. So I've got looking at some past papers. All I ask is that you hit the subscribe button. That would be fantastic, to just show your support. And as long as people keep watching them and keep subscribing, then I will continue to make them. Also, if you want your own copy of these, you can purchase them from the link in the description box. They're great value for money, and they can be used on your smartphone or your tablet. They can be used on the move. You can even print them off and use them as part of your revision notes. So you're more than welcome to do that if you just click on the link in the description box, and you can get a hold of them there. Okay, so like I say, this information here is dedicated to the EDEXCEL specification, and you can see it's split into 3 main topics. So you've got mass spectrometry, which we'll look at first. Then we look at nuclear magnetic resonance, which is NMR, and chromatography as well. And we look at combining the techniques, so combined techniques of some of the spectral techniques that you need to know, so some of the spectral analysis that you need to know. So we'll look at combining them as well. Okay, so the first thing I'm going to do is look at mass spectrometry. So mass spectrometry is used to find the molecular mass of a compound. So that's the relative molecular mass, which is the MR. And it actually has a spectrum, as you can see on the left there, of various lines, and the lines correspond to fragments of the original molecule that we've actually put under test. And so we give it something called a mass to charge, or MZ ratio. And so MZ is just the mass of a fragment divided by the charge. So as most have a 1+ charge, then this is just obviously the same as the fragment mass. So for example, if we have a MZ of 45, that means that the mass must be 45, and if this fragment has a 1+ charge, then what this means is that the 45 divided by 1 will just give 45, so it's just the same as the mass of the fragment. The peak at the end here, called the M+ peak. So the M+ peak shows the actual is the mass of the original molecule that we had before it was put in the mass spectrometer and it was broken up into the fragments. So this is also known as the molecular ion peak, and basically this tells us the relative molecular mass of the molecule. So in this case, we can see here that this molecule has a relative molecular mass of 50 because the M+ peak is here. So it's the most significant peak to the right, furthest right in the actual spectrum. So this is an M+ peak here. Okay, so we can also look at something called high resolution mass spectrometry. So high resolution mass spectrometry is really useful when we're identifying different molecules with the same molecular mass, rounded to the nearest whole number. So you might, for example, have 2 molecules with a mass of 47. So having a molecular mass of 47 doesn't necessarily identify what compound you've got, mainly because there's a lot of different compounds with a molecular mass of 47. And so therefore what we can do is use high resolution mass spectrometry, which is used to effectively help to distinguish between molecules of the same mass. So high resolution mass spectrometers, they measure the relative mass to several decimal places. So unlike the standard low resolution ones, which can only measure them to the nearest whole number, so they're much more precise in terms of the numbers that they give. So let's have a look at an example here. So we've got ethanol, which is CH3CHO, and propane, which is C3H8. They have the same molecular mass, an MR44 to the nearest whole number. Now, in a low resolution mass spectrometer, this means that you wouldn't be able to distinguish between these two molecules in particular, because they would just give the same molecular ion peak. The M plus peak would be at 44. So the way around this is actually using atomic mass data to measure the individual atoms to distinguish between the two. So, for example, we use that data to measure the exact mass of carbon-12. Now, this one is going to be to 4 decimal places. So you can see here that the mass of carbon-12 is exactly 12. So that's 12.000. Hydrogen is 1.0078. Oxygen is 15.9990. So these are the exact masses of each of the elements that make up some of these compounds in here. So you can see let's have a look at the molecular mass of our ethanol here, which is our aldehyde. So we've got 2 lots of 12, okay, which is our 2 lots of carbon. We've got 4 lots of 1.0078, which is your hydrogen, and then we've got our oxygen here as well. So if we add that up, this gives us a mass of 44.0302. Now, if we do the same for CH3C8, so this is your propane, we do exactly the same. We've got 3 carbons and 8 hydrogens, and that gets us 44.0624. So we can see here there is actually a difference, and because there's a difference in the mass, we can actually identify which one could be ethanol and which one could be which one is propane by just looking at the figures to 4 decimal places. So see, with the standard resolution or the low resolution mass spectrometry, these would both turn up as 44, but obviously using the high resolution one, we can actually distinguish between them. Okay, so we're going to look at something called NMR spectroscopy. So NMR is quite a difficult concept, and what we're going to try and do is explain how an NMR machine works, and then what we're going to do is we're then going to look at how we can interpret the spectra, the different types of NMR machine, how we can interpret the spectra, and then obviously try and identify some molecules. So we're going to start. It is quite tough. It's probably one of the most difficult aspects of chemistry, is trying to understand NMR and interpret their spectra. But I hope that we can try and simplify it a little bit more by talking through the information that's on these slides here. So just before I start, actually, NMR machines are used in hospitals quite a lot, but they call them MRI instead. So they don't use the word NMR. So can you think why they've changed the name, even though the instrumentation is the same? Or, the actual analysis of it is the same. So do you know why they've actually they've changed it to MRI instead of NMR? So I'll tell you that towards the end of the video. I'll tell you the reason why. So see if you can have a think. It's a bit of a strange one, beyond the obvious, obviously, but it's a bit of a strange one. So nuclear magnetic resonance, NMR, is used to help determine the structure of a molecule. So unlike some other spectral techniques where they don't really focus on the structure, they look at functional groups, or they're going to look at mass fragments, or they're going to look at say we're going to do elemental analysis, where they're looking at the different types of elements that's in there. This one is NMR is much more useful for actually determining the structure, so it can actually determine or distinguish between isotopes, for example. So there are 2 main types of NMR. So there's carbon-13, which tells us information on how carbon atoms are arranged, and there's high-resolution proton NMR, which tells us information about how hydrogen atoms are arranged. So there's 2 types. So we're going to start with saying that if an atomic nucleus has an odd number of nucleons, which is protons and neutrons, then it has a nuclear spin. Okay, so the nucleus is obviously in the middle, and these nucleons spin in a particular direction. So you can see with the diagram there, trying to illustrate that. And so this nuclear spin actually creates a weak magnetic field around it, and the NMR machine detects how these magnetic fields are affected by a larger external magnetic field. So what we've got is our nucleons spinning in a particular direction, and they've got a mini magnetic field around them here. Okay, and obviously that can be influenced by another magnetic field, an external one. Okay, so as long as you know that. So this is looking at an odd number of nucleons. Okay, that's going to be quite critical, because we'll look at that later in terms of the type of spectroscopy that we're going to look at. Okay, and so hydrogen has one proton, and so it does have a nuclear spin because one is odd, it's an odd number. So carbon normally has six protons and 6 neutrons. However, some of the carbon, so about 1% of the carbon is actually carbon-13, which is clearly an odd number because it contains 7 neutrons and does have a nuclear spin. Okay, so when we're looking at different types of NMR, you can see that we've got two main types. There are other types as well, but two main types is carbon-13, which is an odd number because we're looking at we're only going to be looking at carbon-13 spectroscopy because carbon-12's got an even number, so that doesn't work. Even numbers don't work in NMR. And we've got high resolution NMR, which is a proton NMR, so protons are obviously odd numbered as well because they've only got one in there. Okay, so these nuclei, what they do is they spin in random directions. However, when an external magnetic field is applied, they align in 2 directions. Okay, so this is, remember, all this bit here is just going into how an NMR machine works. The reason why this is important, looking at how an NMR machine works, because if you understand how it works, then it makes it a little bit easier to understand or appreciate what these machines can do, and also how we can interpret the spectra and what the spectra actually means. So, nuclei, they spin either in the direction of an external magnetic field or they spin against it. And those that spin in the direction of the field have a lower energy. So if we have a look here, just first at nucleons. And nucleons spin in all sorts of directions and different orientations. And so the arrows you can see on that diagram represent arrows, the nucleons spinning in random directions. And there's no external magnetic field applied here, so they're pretty much doing what they want. Okay. Energy is, you'll see this diagram drawn in a bit, where we have the nucleons that are aligning with or against the external magnetic field. But you'll see that actually there is an energy line here. So the higher up we go in terms of this space here, then the more energy these nucleons have. So for example, this nucleon has a higher energy than this nucleon down here because it's higher up. This is going to become more relevant in this section here. Okay, so let's have a look. So what we're going to do is apply an external magnetic field to these nucleon and see what happens. So remember, you've got some that will align with it and some that will align against it. And so these ones are, these ones that are aligning with it have a lower energy level than those that are aligned against it. Okay, that's obvious. Remember, if you've seen my other videos, then you'll know that I always say that atoms and molecules and nuclei, or for example, neutrons and protons, they are incredibly lazy, and they always want to be in the lowest energy form possible. So to have these orbitals here, to have these nucleons spinning at a higher energy level, that's not a stable form. But they will obviously they will align against if they're aligning across in that direction anyway. And obviously there's a magnetic field that's forced them into a fixed direction. And so what NMR does is it fires out radio waves and a specific frequency. At a specific frequency, the nuclei are aligned with the magnetic field, absorb the energy, and they flip up into the higher energy level against the magnetic field. So we put energy in to put these nucleon in a higher energy state. Okay, so we use radio waves. So the NMR machine, first of all, applies an external magnetic field, and then it uses radio waves to effectively move some of the nucleon from a lower energy to a higher energy. Okay. So, those with a higher energy, so those at the top there, these can drop to lower energy and they can emit radio waves as well. So, they move up and they move back down again because they want to be in that lower energy state. But as they do that, they emit this radio wave. And then initially, there's more nuclei aligned with the magnetic field. So, there's a lot more there because that's the lower energy, remember. So, overall, more energy is absorbed than is emitted, okay, because we've got more actually being migrated up into the higher energy level, and so therefore NMR is measuring the amount of energy that's been absorbed. So it's in how much energy was required to move these nucleons up into the top level. Now that gap, the difference between that, so remember this is nucleons within one atom, okay, so the difference between here and here is very much dependent on where this nucleon is near to. So it's influenced by other nucleons down. So for example, if this is a carbon atom, these are the nucleons within a carbon atom. If that carbon atom was bonded next to another atom, say like an oxygen, that oxygen would have an influence on how easily the nucleon in the carbon atom moves from the lower energy to the higher energy. So this gap can change, and obviously this is then where we start to use NMR's strength, and actually we can determine, depending on what the gap is here, we can determine what's next to that carbon atom. So this is where we can say NMR can detect or tell us a little bit more about the structure of the molecule that we're looking at. Okay, so just carrying on with that, so the energy absorbed by the nucleon, like I say, is dependent on the environment that it's in. Okay, so everything to do with NMR is mainly to do with what's around the atom that we're looking at, rather than the actual atom that we're actually investigating. So it's very much dependent on that environment. So the reason why is we can get a nucleus can be shielded from external magnetic field from electrons surrounding that nucleus. So for example, remember we've got an atom with a nucleus in the middle, and around that nucleus we have electron shells. Now them shells effectively act as a protective mechanism. So they protect the nucleus inside from the external magnetic field. So for example, if we've got a lot of shielding around there, then it's going to protect it a lot more. If it hasn't got as much shielding around there, then it's going to protect it obviously a lot less. So it's a little bit like, I suppose, if you put if you roll down a rocky hill, for example, I wouldn't recommend this, but if you roll down a rocky hill with no protection on at all, so you've just got clothes on, then that's going to hurt quite a lot because you're going to feel every bump and everything. If you then decide, okay, I'm going to do exactly the same, I'm going to wrap myself up into in bubble wrap, let's say, so you put some protective coatings around you, then actually you can roll down that hill and you're probably not going to feel the bumps as much, so because you're shielded from the effects of that external, the rocks effectively. So NMR is exactly the same, except our protective mechanism is the electrons around that, which is sheltering the nucleus in the middle. But this protective layer can be influenced by being next to something else, another atom, which can perhaps take some of that protective layer, such as an electronegative element that can pull them electrons away from the atom that's shielding the nucleus, and that can have quite an influence on how much the external magnetic field affects it. So let's carry on. So atoms and groups of atoms adjacent to that nucleus, like I say, they affect the level of shielding. So for example, I mentioned this before, but electronegative elements such as oxygen near a carbon will reduce the electron shielding on the carbon atom. So an oxygen will pull some of them electrons that was shielding the nucleus in the carbon atom and pull it towards the oxygen. So that means that carbon now is more susceptible to influence from the external magnetic field. Okay. So I hope you're following so far. Okay, so the magnetic field will be felt, like I say, by the nuclei differently, depending on the environment it is in, as they absorb different amounts of energy and various frequencies. Okay, and so it's the difference that the NMR spectroscopy is picking up. So remember, it's the NMR machine is measuring the absorbance, how much energy it requires to turn one of the nucleons with the magnetic field into the higher energy level. Excuse me. So obviously, depending on the shielding, what affects that is the shielding, and the shielding is impacted by what that carbon atom or hydrogen atom, because this is the type of NMR we're looking at, what that's actually next door to, because that will obviously affect the level of shielding. Okay, so I hope that's making sense so far. So that pretty much explains it, but just to finish off on the actual mechanics in terms of how the machine works, the environment is determined by the groups of atoms that exist near to the nuclei being examined, and we look along the full chain, not just the atoms immediately bonded to the atom being examined. So it's a little bit like if you've got a street, okay, and you've got, for example, if you've got a neighbour that's perhaps cutting the grass at the front of the house, okay? So you might have other houses down the street which are influenced by that person. They might think, oh, they're cutting their grass, so I'll cut mine as well, or I'll cut my hedge, or whatever you're going to do. So so you can see that actually a street is a bit like, each house is a bit like a carbon atom. okay, all the way down the street. And so therefore, somebody cutting the grass say at number 1, where may influence somebody at number 3, which is next door, and that may then influence somebody at number 5, or even number 27 further down the road might actually then have an influence on what number 1's doing. So you can see that there is an influence in terms of a street. It's a bit like a long carbon chain. So carbon chains are exactly the same. You've got one carbon atom, but it is influenced by the full range of molecules down the carbon chain and down the other way as well. So there's a lot of influence here, and we'll see how this fits in later on. But for an atom to be in the same environment, it must be bonded to an atom or group of atoms that are identical. And we'll look at some of the next slides will help us to identify this. So basically, if we've got, say if you've got a house, so you've got one house, and it's only a house with three houses, and only a street with 3 houses in. So you've got the house in the middle, and that's going to be next door to another house, and then next door to another house. Okay, so left and right of each other. So that house is in the same environment because it's next door to 2 identical houses left and right of it. Okay, and there's no other houses around, so you can see there's actually a level of symmetry. So you can see the 2 houses either side are in an identical environment. However, if you look at the end house, one of the end houses, that's not an identical environment, because to the right of that house there's green space, and to the left there's another house, and then to the left again there's another house. So it's the one in the middle that's in the same environment, but the ones on the end are obviously in the same environment for them, because they've got green fields to one side, and then they've got the house in the middle to the other side. So if you can try and imagine that, and this is exactly the same principle with carbon and proton NMR, is where all we're doing is we're looking at what's next door, what's influencing that carbon or hydrogen in the middle. Okay, so we'll have a look, because I think the best thing with these is to actually have a look at some examples so you see what I'm talking about. But this is going to be quite critical, because carbon environments, or identifying environments, is going to be really pivotal in terms of you understanding NMR. Okay, so let's have a look. So we're going to look at some examples at looking at how we can identify carbon and hydrogen environments. Okay, so let's have a look at this one. So this time we're looking at carbon-13 NMR. Okay, so we're not looking at protons. We'll look at protons later, but we're looking at carbon-13 NMR. So you can see here we've got a molecule. Okay, and I've color-coded the carbons to show you where these environments are. So we can see this is a bit like a house, a little bit. So you can see here we've got this carbon here is in one environment. So it is bonded next to a CH3 and a CH3 either side, and it's got a Br and it's got a hydrogen. So we look immediately left and right. Okay, so that's one environment. These ones here are in the same environment, and the reason why, this is what I mean, it's a bit like a house. You've got the end house here, which is next door to a green field. Let's say there's nothing here, and it's next door to this house in the middle, which is CBr. And this house is also next door to, say, green fields, and it's next door to the house in the middle. So these houses on the end are actually experiencing the same type of environment. Okay, so they're both facing onto this middle house, and they're both facing onto green fields either side. So you can see it's the same with carbon. With these molecules here, we can see we've got one environment here and 2 here. So these are both in the same environment. So this molecule has 2 carbon environments, and when we put it through an NMR machine, it will detect it as 2 environments, so we get 2 peaks. Okay, so let's have a look at this one. So all I've done here, and this is what I mean with NMR, it detects structure. So all I've done is I've moved the bromine from middle to the end, and that's dramatically changed what NMR is reading. So now we've got a house here with, say this is a house at the end here. This is now next door to a garage. Okay, so there's a garage on the end of this house. This middle house here is next door to the house with the garage and the house without a garage. And this house here is next door to green fields and a house. So you can see all of them scenarios, each one of them houses are experiencing a different surrounding. So in terms of carbon NMR, you can see here that we've got a carbon, bring it back to from the house. I'm going to stop using the house analogy because I think you might get it now. But basically, we've got this carbon here that's next to a bromine and 2 hydrogens. So that's it there. Next to this carbon here, which is obviously bonded to 2 hydrogens, but it's bonded to a CH2Br and a CH3. And this one is bonded to obviously a CH2 and a CH2Br. So all of these are all in different environments. So they're not a single one of them are in the same environment. So we look all the way across the chain, remember. Okay, let's have a look at this one. So this time we're going to look at hydrogen environments, because we need to know about hydrogen environments as well. So this time we've color-coded the hydrogens. So you can see here we've got these hydrogens. So there's two hydrogens here. So these are bonded to a carbon with a Br, okay, and they're bonded to a CH3. And these purple ones here are a different environment because they're bonded to a CH2 and a Br. Okay, so they're both in separate environments. You see there's no symmetry. Really, symmetry is quite an important one, because if you've got symmetry, that means you've got the likelihood you've got some of these carbons sitting in the same environment. Okay, so let's have a look at the last example. So here, all I've done is added an extra bromine to it, and you can see we now have some symmetry here. So these carbons, these hydrogens, here, are experiencing the same. Are experiencing the same environment. So they're both bonded to carbons connected to bromines. So they're all in the same environment. So the NMR machine would pick up that there's only one hydrogen environment here. They're all experiencing the same, the same environment. So there's four hydrogens obviously in this environment here, and also you can tell it's symmetrical. So where you've got symmetry, you have less. You don't have as many different environments if you've got some symmetry in your molecule. Okay. Right, so tetramethylsilane. Okay, so TMS is a chemical that's used as a standard when we're looking at chemical shift in NMR spectra. Okay, so this is quite important because you're gonna need to know how to spot this and why, and why it shows the peak that it does. So nuclei, what they do is they absorb different amounts of energies at different frequencies, and it's really difficult to measure the magnitude of this without reference to a standard chemical to measure it against. Okay, so you've got to have a reference, you've got to have a benchmark. Otherwise, if you don't have a benchmark, you don't know how much energy is being absorbed. You don't know if that's large, you don't know if that's small. And we use something called tetramethylsilane, or TMS. So, for example, and we do this all the time in science, we've got to measure it against something that we have confidence in, and that we can measure it against to make sure that we can, that if that value is 0, then we can measure that against. So, for example, if I was to say, is an elephant heavy? You would probably say yes. Okay, it's very heavy. If I was to say, okay, is an elephant heavy in comparison to the weight of the Earth? You would say no, it's incredibly light. But the reason why you're probably saying that it's heavy is because in life we benchmark constantly against something which we're comfortable with, or something which we know. So, for example, if we're looking at life, we maybe look at a car, for example, or we look at shopping, or we look at picking up objects every day, like a computer, like a pen. And all these things are quite light relative to us. So when we look at other objects, what we use every day, we compare them to them and we say that it's heavy. Now, that's fine, but one person's heavy is another person's light. So it's really difficult to actually justify these comparisons. So in science, we have a standard and we have a reference that everybody uses, and everybody sticks to that same standard, that same reference. And that means that if a scientist in Germany does this, and a scientist in Britain does this, or a scientist in America or Japan, or anywhere around the world, they know that actually they're all being measured against the same standard, and we can have confidence in comparing results. Okay, so we use TMS. So that's just with anything in science. Obviously, it's not specifically to this, but obviously, this is a standard. But anything where we're measuring something, we have to measure it against something. We have to keep some things the same and change one thing. So it's so important. Otherwise, you get results which don't mean anything. So tetramethylsilane has this structure anyway. So we've got a silicon molecule, silicon atom, in the middle here, and we've got methyl groups around here. So hence the word tetra, meaning 4, methyl, because we've got methyl groups in silane, obviously with the silicon in the middle. So TMS has 12 hydrogens, all in the identical environments, and this will produce a really large single peak, well away from other sample peaks. Okay, so and the good thing about TMS is that it's inert, it's non-toxic, and it's volatile, so we can remove it from our sample. So we mix our sample with TMS, but we basically calibrate our NMR machine to make sure that this TMS peak is 0, and then everything else is measured relative to that. So that's a standard recognized chemical to use in NMR. And so the difference between the TMS peak and the peaks produced by the substance under the test is called a chemical shift. And what you'll be given in the exam is a data book or a data sheet, and that will have your chemical shift tables on there. So you don't need to remember them, but you will see some examples in this video. So we measure chemical shift in parts per million, so ppm, as because it's used as a standard to measure against, we assign this as sigma 0. Okay, so we say that it has a 0 value, and it means that everything else is measured relative to that. So when we look at an NMR spectra, you'll often see this peak at 0, as TMS is used to calibrate your NMR machines when analysing a sample. Now you might find it might not be the biggest peak, probably won't be. You can actually alter an NMR spectra to emphasise peaks that you want to know, but the peak at 0, and if they ask you, any peak at 0 has got to be because of TMS. It can't be because of anything else. Okay, so the peak at 0, no matter how high it is, must be because of TMS. Okay, now you can see here, just coming back onto TMS, the reason why, you can see we've got symmetry here. All of these carbons here and all of these hydrogens are all bonded to the same silicon, so they're all in the same environment. Okay, so that's why we get this nice strong peak. It's very rare you're going to get chemicals that you're testing that will have this level of symmetry, so that's why we use this chemical. Okay, so let's look at carbon-13 spectroscopy. So carbon-13 NMR spectroscopy tells us how many different carbon environments there are in the sample being tested. So that's what we're going to look at first. So then we'll look at proton NMR later. So the peaks on a carbon-13 NMR spectrum, they tell us the number of different carbon environments in our molecule. Okay, so it's fairly straightforward. Proton NMR tells us a little bit more because you have splitting patterns and etc. But we'll look at that later, so don't worry too much about that now. Okay, so we have a carbon-13 spectrum here, and this is the spectrum of this molecule, which is chloroethane. So each carbon in the molecule is in a different environment in this molecule. We'd seen something similar in the previous slide, but we had bromine on the end. So we know we've got two different environments here, and they have a different amount of electron shielding. So for example, remember that when we're talking about influence of other atoms, this carbon has electrons around it, and what NMR is doing is it's exciting the nucleons. They're in the nucleus in the atom, but around that atom we have electrons, and that shields the external magnetic field. So this chlorine is electronegative. So what it's doing is it's pulling electrons away from that carbon in the shell there, and effectively this carbon is now more exposed to the external magnetic field, and as a result then the energy difference is going to be different, so the shift's going to be different. Whereas this carbon atom here is further away from this chlorine. There will be some electrons maybe pulled away from the shielding in there, but nowhere near as much as this, okay, because it's further away from that chlorine, so it's not influenced as much. So what this does is this transpires into our spectrum. So we get ones which are influenced the most are going to be shifted the most because they're going to be affected the most. The ones which are further away from the source of influence are not going to be shifted by as much. So let's have a look. So the red carbon, this one here, okay, this is the one that's closest to the electronegative chlorine. So this one is going to have, the shielding is going to be a lot lower in this carbon because it's been pulled away by the chlorine. And so therefore the chemical shift is going to be high, and you can see on that graph there on the spectrum that the peak caused by that carbon is a lot higher up. Now obviously the other peak there, the green one, is the one that's not shifted as much. It has a lot more shielding in the carbon, so therefore it's not shifted as much at all. Now you can see there's a little peak at 0, so that peak of course is because of TMS. Okay, so make sure you're aware of that. It doesn't have to be the biggest peak, it just has to be the peak at 0. Okay. Okay, so carbon-13, like I say, the carbon-13 tells us how many different carbon environments there are in the sample being tested. So, and we're going to look at cyclic compounds in particular for this example, because we looked at aliphatic carbon. They're just the straight chain ones. So now we're going to look at cyclic ones. They're a little bit more difficult to predict because they're cyclic, so they don't have they don't have a straight chain where you can easily identify differences in the carbons. So this case, we're looking for symmetry. So here's our molecule here. And here's our cyclic compound. We've got 2 chlorines on here, and here's the spectrum for it. So you can see we've got a lot more peaks there. So what we're looking for is any symmetry in this molecule, and we're looking for what peaks will this produce. So let's go through it. So you can see here we have got symmetry straight down the middle there. So there's our symmetry. So I suggest when you get molecules like this is that you draw your line of symmetry. So in this case it's 1,3-dichlorocyclohexane, and then what we do is we look for the number of different carbon environments, and we can see here that actually we do have 4 different carbon environments. So we have one here, and we have these ones are in the same environment, these ones are in the same environment, and this one is in a different environment. So what we're looking for, and we'll circle them and see where they are. So you can see there's the first one. So this is the one that's actually it's a single carbon on its own, but actually if you look what's left and right, so we've got a carbon with a chlorine and a carbon with a chlorine, okay, and then we've got carbon hydrogen, and carbon hydrogen. So that one's one environment that's quite unique because it's sandwiched between these 2 CCl bonds. The next 2, so it's these 2 red ones here, these are in the same environment, and that's that peak there, okay, in our spectrum. So this is a bigger peak. It's much bigger. This carbon is shifted quite high because it's bonded directly to the chlorine. But also, you can see here that these 2 are in the same environment because they're both bonded to chlorine. They're both bonded to this carbon in the middle, and they're both bonded either side here. You can see there is symmetry there. So if we go right across that carbon chain, they're exactly the same. Okay, so these 2 here are different environments. So that's this peak there. Okay, so this is these carbons are bonded, both of them. You can see the symmetry. They're both bonded to a CCl bond. They're both bonded further around to this carbon, and they're both bonded to that same carbon there. So these ones are actually in the same environment. And finally, the last one, the orange one here, is that peak there. Obviously, that's on its own. This one at the end here is different to that one because this one is not bonded to a CCl. Okay, this one is bonded to a CCH and a CCH and going round. Okay, so it's as simple as that, really. It is a bit trickier. You've just got to be methodical. Look for symmetry. I find it easier to draw your symmetry line first, see if there's any symmetry, and then look for your carbon environments from there. Obviously, that last peak there is TMS as well, so no difference. You'll always get a TMS. You'll always get a peak at 0, and that's your TMS. Okay, so carbon-13 chemical shifts, they have values, and carbon environments can be determined. Okay, so this is what I'm saying. You'll be given this data in a data sheet or a data book. No, more than likely, you'll just have a sheet with this data on. So you will be given this. You don't need to actually remember the information on here, but it might not be exactly the same as this, but it'll be something similar. Okay, so you'll have your chemical shifts, and you've got your type of carbon environments. Now you can see here what I've done is I've highlighted the carbons that is actually causing the shift in red. So you can see here, there, and there, and there, and there, and there. So you can see all the way across, apart from your aromatics, of course, because that is just carbons. But we are highlighting the particular carbon that's actually causing this. On your sheet, it might just be in bold, so that's why you'll find some of them are actually in bold. Okay, so what we can do is we can match up the position of the peaks in the spectrum to the table, and we can work out what carbon environments exist. So it's fine, obviously, knowing the different carbon environments, but we can actually start to identify what type of, what could that carbon be next to that's causing it to shift like that. So there are some issues, though, as this is science. There's always going to be problems and limitations. So we've got a peak at 190 so a peak at 190 will suggest a carbonyl group. However, we can't be sure if that's an aldehyde or ketone. So it's not quite that sophisticated enough to work out exactly what it is. And also there are overlaps at a peak at 60, and this could be because you've got an amine, or it could be an alcohol, or it could be an ester, or it could be an ether. So there's quite a lot of different possibilities there. So it hasn't narrowed it down massively. And this is why, as you'll see, coming towards the end of the video, we'll look at combined techniques. It's about using NMR with other machines as well to make sure we can identify the compound that we've got. Okay, so for example, let's say a chemical has the formula C3H8O and its spectrum is shown below. So we've got the spectrum there. What is the displayed formula? Okay, so that's all we've been given. Okay, we've been told what its formula is, a molecular formula, and we've been given the spectrum, and we have to work out what this is. So the first thing we have to do is draw down all the possible isomers of C3H8O. Okay, once we've got that, we can then start and eliminate from them. So here they are. So here's our three isomers, so three possible ways in which we can arrange our C3H8O. So then what we have to do is we look at the number of peaks, and you can see in this spectrum we've got 3 peaks. So this means that we must have 3 different environments. So this rules out propan 2-ol, as this only has 2 environments. So let's have a look. That one there. Okay, so you can see here I've color coded them, but you can see there's only 2 environments in here. So this spectrum cannot be propan 2-ol. Okay, so we have 2 peaks at 65 and 75. Okay, and so this suggests that the 2 carbons are bonded to an electronegative element such as oxygen. Okay, so this fits the structure of an ether rather than propan 1-ol, where we'd only see 1 peak in this area. So we use that data table that we'd seen before, or the one that you've got in front of you, and we try and say, right, what is these, the peaks at these values, what is actually causing this? So you can see here that in this case, it is going to be our ether that's the likely structure for this, rather than our alcohol, our primary alcohol. Okay, so that's how you do it. You basically just look through. Now you'll have loads of examples here, and the key thing with NMR is practice and practice and practice. And you'll get the hang of it. It's good marks in the exam. You just need to be familiar with how you work it out. Obviously, carbon-13 is fairly straightforward, relatively speaking, to proton NMR, but nonetheless, you still need to be vigilant. You still need to be looking out for the shift patterns. You need to know what the peaks mean, and you need to know, obviously, you need to know how to identify structure from them as well when you're given the molecular formula. Okay, so let's look at the other type of NMR, which is Proton NMR. Now, Proton NMR is a little bit more trickier. There's extra features to Proton NMR. It's a bit like an iPhone, I suppose, or a new Samsung, so a new Galaxy. So you've got extra features that are added to this, and it has its advantages and it has its disadvantages still. It's not perfect. So let's have a look at what this is. So Proton NMR spectrum, a spectroscopy, tells us how many different hydrogen environments we have, and it tells us how many hydrogens we have in that environment. So this is good, because carbon NMR didn't tell us exactly how many carbons are in that environment. It just tells us there are this many environments. So Proton NMR has got a little bit more detail here. Okay, so the peaks on a proton NMR spectrum tells us the number of different hydrogen environments. Okay, that's exactly the same as carbon NMR. Okay, so the number of peaks tells us the number of hydrogen environments, except we're looking for hydrogen, of course. Okay, so we've got our molecule here. So this is ethanoic acid. Okay, so we've got a carboxylic acid here, and we have the NMR spectrum for this here. Now, you can see we've got numbers above the peaks in this spectrum, and this tells us the ratio of the areas under the peaks. Okay, and this allows us to work out the relative number of hydrogens in each environment, and sometimes these numbers can be decimals. So we call this an integration trace, this red line. So what we do is we measure the area under each peak, and the area under the peaks tells us how many hydrogens are in that environment. But quite often that can be really, really difficult to actually measure the area under the peak. So what we do is you'll find in a lot of spectrum NMR machines, they will actually put numbers above the peaks, and that tells you the relative area of that peak relative to the smallest peak. So this is telling us that this peak has a value of 1, this peak has a value of 3. So this is telling us we've got a 3-to-1 ratio here. Okay. So you can see in ethanol we have 2 hydrogen environments. So we've got 1 at the end there, which is in red, and obviously the green ones have been circled. That's this one here. So we have 2 different hydrogen environments. So the number of peaks tells us the number of hydrogen environments. Obviously this peak is caused by TMS. That's the standard one at the end. Now the peak on the left, This one has a value of 1, like I say. The peak on the right has the value of 3. So this means there's 3 hydrogens in one environment, and there's 1 hydrogen in the other environment. So there's a 3 to 1 ratio. And you can see actually this fits with the structure here. So you can see the green circles here, they've got 3 hydrogens. They're all bonded to the same carbon, which are then bonded, further on. So they're all in the same environment, and this hydrogen is on its own. It's directly bonded to an oxygen, and there's no other hydrogens in here that's bonded directly to an oxygen. So that has its own peak. This one's shifted well up to the top. Obviously, remember from last time, from the carbon NMR, this is heavily shifted because, look, it's literally bonded directly to that oxygen, so it's ripping the electrons away from it. So it's really exposed to that magnetic field, that external magnetic field, and that's why it's shifted well up to the top of the spectrum. Okay, so like I say, that red line is the integration trace, and it shows the area ratio of the peaks, as I've mentioned before. Okay, so just like carbon-13 spectrum, you also have proton NMR data as well. So it's separate data. Don't get them mixed up. Carbon-13 data will have larger numbers on them. Your proton NMR data has smaller numbers, so that's the main difference. And the other difference as well is obviously these are detecting hydrogen environments and not carbon environments. But the principle's the same. We're still using it in the same way. So you can see here that all the hydrogens that are actually being affected in question are the ones in red. So you can see you've got an alcohol here at the top here. So this is the hydrogen that we're talking about, and then the other hydrogens in the molecules all the way down. And this is going to be quite interesting and useful because you'll see when we actually look at analyzing spectra, this is going to become quite pivotal in terms of trying to determine that. Okay, so here we've got a previous spectrum of ethanoic acid. Okay, and we have a peak at 11.7, remember, and then a peak at 2.1. So this peak at 11.7 is actually telling us that it's a hydrogen. What's actually causing this peak is this hydrogen that's bonded to the oxygen. So that tells us straight away we have a carboxylic acid because it's shifted right up there. And then this peak here, the one at 2.1, is because of this here. So this is telling us we've got a hydrogen. It's this hydrogen here that's bonded to a carbon, that is bonded to a carbon with a double bond O group on. Now that would make sense because this double bond O is actually coming from this here. Okay, so if we put the two together, it's telling us that we have a hydrogen next to that, and actually we know we've got our carbonyl group here, so actually that hydrogen has clearly got to be where that R is there. Okay, so that's how you work it out. It's just about trying to piece it all together. Okay, so proton NMR spectrum have peaks that split. Okay, this is where it gets a little bit complicated, but it's going to be fine because we'll talk through it and we'll work through it and break it down as simply as we possibly can. So this allows us to actually determine the structure. Now this is immensely powerful for chemists, so it's a really good way of determining if we've made a molecule that is an isomer, or if it has isomers, which isomer is the correct one. Vital in medicine, of course. So let's have a look. So peaks that split into smaller peaks are known as a splitting pattern. Okay, and so the number of smaller peaks corresponds to the number of hydrogen atoms on the adjacent carbon plus 1. Okay, and we call that spin-spin coupling. Right, so this is a bit tricky, isn't it? So this rule is called the N+1 rule. Okay, so let's go through it. We'll go through it step by step, okay? So what we're looking at here, remember what we said with proton NMR, is it's mainly all about what's next door to the carbon, not the actual, or the hydrogen. It's not actually what the hydrogen itself in question. So we're always looking about, okay, what's next door? So it's quite a nosy form of spectroscopy. So what we're looking for is we get different types of splitting pattern, and we call these splitting patterns either singlets, doublets, triplets, quartets. Okay, so basically the peaks that we've seen, and you've seen one single peak, these peaks can be split into smaller peaks, but you can have more of them. So for example, a single peak can be split into 2, or it can be split into 3, or it can be split into 4, and depending on what it splits in is dependent upon what's next door to that. Okay, so let's have a look. So a singlet peak, what this means for the hydrogen in question that we're looking at, a singlet means that we have a hydrogen, but that hydrogen is next door to no other hydrogens. okay, on the neighbouring carbon. So, for example, you know that carboxylic acid that we'd seen, and we had that lone hydrogen, and it was directly bonded to the oxygen. That hydrogen would give a singlet peak because it's bonded to an oxygen. It's not bonded to a carbon at all, and so therefore that would be a singlet peak. Okay, so that would definitely be singlet. A doublet is where we have a hydrogen that is bonded. So the hydrogen on the carbon is bonded to another carbon with one other hydrogen on it. So that gets us a doublet. A triplet peak is where we have a hydrogen in question that's bonded to the carbon, and so that is bonded to a carbon with two hydrogens on there. So that could be a CH2, for example. And a quartet is where we have three hydrogens on the neighbouring carbon. So what we're looking at is what is neighbouring it, what is next to it. So how many hydrogens are next to it, and we add one. So we plus one, okay? So let's have a look at an example. It's always easier to look at an example, I think. So here we've got ethanol, okay? So ethanol has two carbons, and obviously you've got your OH group on the end there, okay? So you can see we have three different peaks here. So we've got hydrogen, hydrogen, and hydrogen. Okay, so you can see in terms of identifying them, we have an OH peak, a CH2 peak, and a CH3 peak at the top there. So the hydrogen on the OH is bonded to the oxygen. Okay, so this is not a carbon. Okay, that's the first criteria. If it's not bonded to a carbon, straight away that is a singlet peak. Okay, so this is not a carbon. So the neighbouring hydrogens is 0. So if we apply this n+1 rule, that's 0, because there's no carbon there. It's not next to any carbon. 0 plus 1 is 1. That's a singlet. So in fact, that's what we get. We get a singlet peak that's been generated because of the hydrogen on the OH. Okay. So let's have a look at another one. So the hydrogens on here, these CH2s, okay, so the hydrogens on here are adjacent to one carbon that has three hydrogens on. So you can see this here has it next door to an oxygen. That's not a carbon, so we just ignore that. So we look to the left of it. We've got a carbon there, and this carbon has three hydrogens next to it. So this means if we apply the n+1 rule, 3 plus 1, it's 4. So we get a quartet. So these hydrogens here will produce a peak, and that peak is split into a quartet. So that's it there. So this quartet is telling us, so if we go backwards, this is telling us that this CH2 is bonded to something, a carbon, with three hydrogens on. Okay, and then let's have a look at another one. So the final one, so these three here, so the hydrogens on CH3 are adjacent to one carbon. So there it is, there's your one carbon. And this has two hydrogens on. There they are. Okay, so if we apply the n+1 rule, we get 2 plus 1 equals 3, and this is a triplet. So the peak caused by this one here, this one is actually split into 3 because it's neighbouring a carbon with two hydrogens on. So n+1, so that's the 3, and you can see there's your triplet. So you can see how this actually structures and how it works. Now the key thing with this is just practice, because obviously it's all well and good looking at it and say, yeah, you understand it, but you know, if I was to put an NMR spectrum in front of you, could you do it? You'd probably give it a good go if you look through this video and follow the rules. But the key thing is just practice and just get used to practicing with different types of molecules. I think that's the key thing here. Obviously, this is an alcohol, but do it with a carboxylic acid. Do it with an ester. Do it with an amine and an amide, and do it with all these different types, and just make sure that you're familiar with the types of functional groups in here, because that's what's really going to cause the most influence here is functional groups. Okay, so remember we looked at the integration traces before, and we showed this. So the integration traces shows the areas under a peak more clearly. And what this does, it actually helps us to work out that hydrogen ratio. So they might get you to actually work out or use the integration traces to put the numbers in the first place. Okay, so let's have a look and see how we do it. It's pretty straightforward, to be honest. But when we have split peaks, it's difficult to work out the area under that peak, remember, because if you have a quartet, how do you then measure the area under that? It's just too difficult. So what the NMR machine will do is it's really helpful, is it'll put an integration trace in for us. And basically what it's doing is it's converting the area under that peak into a height ratio instead. So it's converting it into a different metric. So in practice, what we do is we use a ruler to measure the vertical parts of the trace, and we write the lengths down and use these numbers to come up with a ratio. So that's basically how we do it. I remember being at uni doing things like this. It was quite a while ago now since I was at university, but going through these, sitting down, and really, analysing this. It's a little bit like a crossword or Sudoku puzzle or something like that. So it's actually quite therapeutic, believe me. So all you do is you get your spectrum. So we had NMR spectrum, but we weren't told the numbers. We had to work them out ourselves. So this is exactly what I did. So in the spectrum, the integration trace shows us a 1 to 1.5 to 1.5 ratio. And so if we round that up to get a whole number, we get a 2 to 3 to 3 ratio. Okay, so it keeps it nice and neat. So this is our integration trace of a spectrum here. And that's basically how we do it. And basically what this does is it tells us that we have 3 different hydrogen environments because we've got 3 peaks. Okay, one with 2 hydrogens in, and the other one has 3 hydrogens in there. So the other 2, should we say? So we've got 2 to 3 to 3. Okay, now this is really useful because you look at that and you think, oh well, that's taller than that one. It's nothing to do with the height of the peak. Okay, it's very important. This has the same number of hydrogens as this one, it's just this one's spread over a larger area. So this red line here, or whatever line they give you, you just measure the vertical parts of it, and that tells you, obviously, the relative ratios. Okay, so let's have a look at some examples here, okay, because the key thing, like I say, is practice, so here we're going to predict the structure of the compound using the data table from this Proton NMR spectrum, and this has a molecular formula of C4H8O2. Okay, now you might straight away think, oh, that's a carboxylic acid. It could be an ester. It could be anything like that, but at least we know the formula. Okay, so it's got 2 oxygens in. And there's our spectrum there, and instead of the integration trace, we've actually worked that out for you already, so very kind, and put the numbers in the top there, so it's 2, 3, and 3. So we can see there's 3 hydrogen environments in the molecule, and with a ratio of 2 to 3 to 3, which is likely to be, we can speculate, but it's likely to be 1 CH2 and 2 CH3 molecules within this group. Okay, that's what it's likely to be. It's always good to get a rough idea, and then at least it sharpens our mind a little bit more. Okay, so we're just, every time we're narrowing it down to what it is. So this is what we think it could be. So we have a peak at 4.1, which is this one here. Okay, this one at the over onto the far left hand side. So the peak of 4.1 has a value of 2, and this suggests a CH2. And if we use the data table, so the data table that we've got in your data sheet, then this suggests this type of structure. So we have that H there, okay, and it's telling us that this H is, yes, it's bonded to a carbon, of course it is, but this is actually bonded to an oxygen, and then next to it is a carbon with a double bond O. Okay, so that's quite interesting. So we've literally glimpsed at a little bit of information. We don't have the full structure, of course we don't, but we know that this hydrogen is next door to this setup here. Okay, so that's given us a little bit of information there. Looks quite like an ester, doesn't it? So the splitting pattern is a quartet. Okay, so what does that mean? Well, that tells us that this CH2 is actually next door to a carbon with 3 hydrogens. Remember, because it's the n+1 rule. So that's likely to be a CH3 molecule. So let's move on to the next peak. So we've got a little bit of information now. We think it's an ester, and we think we've got a CH2 molecule bonded right next to that ester group, and next door to that is possibly a CH3. So that's what we know already, just from one peak. So let's carry on, because we need to confirm this and make sure we're absolutely correct. So we've got a peak at 2.1 here, okay? Has a value of 3, which suggests we have a CH3, that this is a CH3, sorry, and using the data table, it tells us we've got this type of structure. So this is telling us actually we have a CH3, and the hydrogen that's under test is bonded directly to a C double bond O. Right, so this is starting to fit together a little bit more. So this C double bond O, remember we looked in the previous peak, we do have a C double bond O, so it's definitely confirming that. But actually what this is saying is this hydrogen is bonded to a carbon directly bonded to that C double bond O. So that could be this R group here. So we could have a CH3 there on the end. Okay, so this is what it's telling us, but it's not telling us that we've got this and this. That's not what it's telling us. It's telling us that we've got a hydrogen next to a C double bond O, and that's what we've got here as well. So that could be there. Okay, it's very important with NMR not to just add these bits up and get what you know and work it out. It's just telling you what it's next to. The splitting pattern is a singlet. It suggests that this is a CH3 and it's next to a carbon with no hydrogens. Perfect. Okay, so that's telling us that this CH3 is next to a carbon, and that carbon doesn't have any hydrogens. So that's perfect. That really does fit. That's fitting quite nicely. Okay, so let's have a look at the last peak though. This is a peak at 1.2. There's a value of 3, which suggests that it's a CH3, and we're using the data table that we've obviously that you'll have in your data sheet or your data book or whatever you're given actually in the exam. It might even be in the exam paper. I doubt it. It's probably going to be in your data sheet. So and using the data table suggests this structure is an RCH3. It's a triplet peak, which means it must be next to a carbon with 2 hydrogens, okay? So it's likely to be a CH2. Now, we've already identified a CH2 here. So this CH3 that we're talking about is bonded to another carbonyl group, so possibly it could be on the end here. So we could have a CH3 stuck on the end there, next to this CH2, and then we've got a CH3 here on the end, okay? So let's put all this together. So there it is, ethyl ethanoate, circling the different peaks. Okay, so you've got your 2 there, and then your CH3 at the end there, which is obviously caused by that last peak there. Okay, so make sure, once you've drawn your molecule, always make sure you test it. Draw it out and just circle it and see, right, does that actually fit the spectrum that I've got? And if it does, the chances are you've got it right. Well, more than certain you've got it right, okay, because they're not going to give you anything too horrendous. So you can see here that we've got, definitely it fits. We've got a CH3 bonded directly to that C double bond O group. So that was this bit, that's what we're telling us about. It's got 3 hydrogens itself, which it does, that's fine. This one's got 3 hydrogens, which is the one at the end. It's split into a triplet, which tells us it's next door to 2 hydrogens, a carbon with 2 hydrogens, which is fine. Obviously this one's a singlet here, so that's bonded to a carbon with no other hydrogens, that's fine. This one has 2 hydrogens, but it's split into a quartet, which tells us it's bonded to something with 3 hydrogens. So you can see here that we do have the 3 hydrogens. So you can see how that's structured, but practice, practice, practice. That's the key thing. Okay, so let's look at something else. It's a tiny little bit that they've kind of strangely bolted onto the topic. There's not a lot of information you need to know about elemental analysis, but elemental analysis is basically just a method which we can determine the structure of the sample under test. Okay, so very straightforward actually, and it looks like this. So you won't have one in school or college, and if you do, it's clearly got a lot of money. Yeah, it's a bit of a kit. Normally you see it at university, like at universities, for example, and I've used one myself. So they're not that fascinating. But basically what it does is it helps us to determine the percentage composition of the mass of elements that make up that compound. Okay, so fairly straightforward. If we know the molecular formula, we can actually work out the structure of the compound using a machine like this. And basically the data that's produced from the elemental analysis can help us to determine the empirical and molecular formula of a compound as well. So your elemental analysis helps us determine the percentage composition of mass of elements that make up that compound. So you might have seen in topic 18, towards the end, that was a big topic, that one. But right towards the end of the video, or towards the end, then we look at empirical formula and molecular formula. Now, the figures or the data that we used there was percentage figures. So it had percentage of carbon, the percentage by mass of hydrogen, etc., etc. And we used that information to work out empirical formula. Now, them percentages of the elements come from this type of analysis here. So this is probably the only thing why I think they've kind of put it in here. Personally, I think it should have been in topic 18 where you had your percentage analysis and empirical formula, because then it would kind of fit. But I suppose it's it fits into this topic because it is a spectral technique. It's a type of analysis. So yeah, so this is basically where it fits, but it's just to try and bridge the two so you can see kind of where this odd bit fits into the specification. Okay, so we're going to look at thin layer chromatography, because remember one of the parts that you or one of the bits in the specification was that you had to know about chromatography and different types of chromatography. Now you would have seen TLC, thin layer chromatography, for amino acids, so you would have seen it for that section. This is going to look at it in a general form, so in case you're thinking, hang on, have you not done this in a previous topic? I have, but it was to do with amino acids. So we're just going to look at it here in terms of general use rather than just for amino acids. So thin layer chromatography, it allows us to separate and identify compounds. So it's quite useful. So thin layer chromatography uses a stationary phase of silica or alumina mounted on a glass or metal plate, and a pencil line is drawn, and drops of mixture are added. So you can see here we've got a mobile phase here, so which is mobile phase is the bit that migrates up, so it's the bit that moves, and we've got our stationary phase here. This is the phase which doesn't move, so in other words our solid silica here, so silicon dioxide or aluminium oxide based plate here, and then we have a lid on top of this, because what we don't want is a solvent to evaporate from our beaker. We want it to remain in the beaker. So what we do is you place the plate in the solvent, and the baseline must be above the solvent level. So very important that we've got our baseline here with our samples under test on the bottom. The solvent line must be below that baseline. Okay, if it's above, then you just end up getting your substances dissolving into the actual solvent, and we don't want that, do we? So leave it until the solvent has moved up near the top of the plate. So we just let it rise gently. It soaks into the stationary phase and moves up and migrates up, and we get a solvent front at the top, and we mark where the solvent front is on a chromatogram, and we allow it to dry once it's migrated near the top. And so then it works really by the mixture spots dissolving in the solvent. Now sometimes these chemicals will actually spend more time adhered to the stationary phase. Sometimes some chemicals will spend more time in the mobile phase, and so therefore they'll migrate further up the chromatogram, whereas the ones which are not very soluble will spend more time stuck to the stationary phase, and therefore will probably sit lower down on the chromatogram. Okay. So we can identify the compounds or the chemicals that make up our mixtures by checking the positions of them at the end and calculating RF value, which is what we're going to look at now. So, like I say, these can be identified using the RF value from your chromatogram. And so the number of spots on the plate, so when you get your chromatogram and it's all dried and finished, you'll see there's a few spots in there. Now the number of spots on that plate basically tells us how many chemicals make up the mixture, okay? So if there's 3 spots, it means we've had 3 chemicals in that mixture. If there's 2, we've had 2 chemicals. Pretty straightforward. And the chemicals, these can be identified by calculating the RF value and comparing these to a library of known RF values. So if we can see here, we've got our chromatogram that's already been produced. So this is the one that we pulled out of our beaker. And you can see we've got a solvent front that's drawn in on the front. And we have the distance that's been travelled by our spot, which goes up the top, up there. So that starts to migrate up. And so basically what we're doing to work out the RF value is we do the distance travelled by the spot, which goes up here, divided by the distance travelled by the solvent, which is this bit here. Okay, we divide them and we get an RF value. And what we do for that RF value is we compare it with a known library of RF values. So, and that can help us to identify what the compound is depending on what the RF value is. However, we've got to make sure that we keep certain things constant and keep certain things the same. So we get different RF values for different chromatograms. So what we've got to make sure is the temperature that this is conducted in remains constant, the solvent remains constant, and the actual makeup of the TLC plate, that remains constant as well. So we've got to try and keep things the same. So when we're comparing RF values, we've got to make sure that we're using the same methodology as what the data book is suggesting. Okay, so pretty useful actually. So we're separating and we're actually identifying as well. Now, that's all well and good. However, you can't actually get hold of your sample once it's on the chromatogram. Once it's on the chromatography paper, we can't get that sample back again. So there is another method of chromatography where we can actually take our products that we've made, and we can actually use them or do something with it so we can separate them out. So gas chromatography is actually a useful method to separate a mixture of liquids that are volatile, and hence these can actually be identified as well. So very good for volatile substances. So a gas chromatography machine, again, you won't have one of these at school or college. They are very expensive bits of equipment. They're quite big bits of equipment as well, so they're sit on a large bench. And they have this general setup here. And we're going to go through each one of these sections of the gas chromatography machine and see what each bit does. So, in the gas chromatography, we have a very thin column that is wound up inside an oven to save space, and the column is lined with a solid or viscous liquid such as an oil, and this actually acts as the stationary phase. Obviously that should be an A. Don't spell stationary like that with an E, so that's if you're looking at pens and pencils. So this should be an A, so I'll get that changed. So stationary phase. So you can see here, here's our very, very thin column, which is in here, very thin column, and lined in that column there, we have a very very thick liquid that's lining into it. It is incredibly thin wire. It's not very thick at all. It's like a bit like fishing wire to an extent. So it's a bit like that. So this is wound up inside an oven. So this is our oven here, and this oven is then obviously heats up the keeps the substance inside the tube warm. Okay, so the sample is injected into the machine. So there's the injection here. So whatever we're using, whatever we want to sample or separate out, we inject it in here. And we use an inert gas to carry it. So we've got a carrier gas here, which actually carries our sample through our column all the way through here. This is the mobile phase and is normally something like nitrogen. So something inert that isn't going to interfere with our mixture or sample that's under test. And so what it does is each substance takes a different amount of time to actually travel through the column, okay, and it reaches the detector. So it comes out and reaches the detector, and our waste then comes out on the other side. And the length of time it takes is called the retention time. So we put it through here. It spends time going through round and round and round, and then it comes out. And then it detects. Every time it comes out here, it detects it and sends a signal to your machine, which then tells you obviously what then tells you the peaks that are formed, and it tells us what the substance possibly could be by comparing with the library. But look at that in a moment. So the time it takes for the sample to travel through varies because some molecules spend a lot more time stuck in the stationary phase. You can see I've got that correct there, so that's the right spelling, so the stationary phase, and some spend more time actually travelling in the mobile phase. So if it spends more time in the mobile phase, i.e. the nitrogen or any other inert gas, then it's going to come through the end of that much quicker. Some substances like to adhere to the solid stationary phase within that tube, and therefore it's going to take a lot longer to actually come through the other end. Okay. And that effectively in itself is a separation technique because we're separating the different components of our mixture, but we can also identify it, which we're going to look at now. Okay, so let's have a look at the spectra that we actually produce. So as you can see, it shows peaks of varying sizes and they appear at different times. So you can see here we've got our time, which is at the bottom, which is there, so that's time in minutes, and we've got our detector response, and here's our chromatogram here, gas chromatography. So each peak here, each peak in the spectra represents a different substance, and each substance has a different retention time. Okay, so you can see here, this is the distance from 0 to 4 minutes. So this is our retention time here. So we can compare that retention time with a library of known substances to identify what we could have in our mixture. So that's pretty straightforward. So the area under the peaks, this tells us the amount of each substance. So the larger the area, the more substance we've got. So you can see we've got a very large area here. So whatever this is, we've got a lot of it in our mixture, and we've got very little of this here. So we haven't got much of this at all. And so gas chromatography is actually really useful because it allows us to detect the amount of alcohol in urine and blood, and this can be used in evidence in court because the results are fairly reliable. So this is where gas chromatography is used in things like forensics, for example, and also for art historians or art restorers, for example, so paint restorers. So they can also identify volatile compounds in paints such as esters, and obviously this is useful for the restoration of the restoration of artwork. So what you want to do is try and imitate as close as you possibly can the paints that were used by the original artist if it needed repairing. So using quite detailed chromatograms like this, we can actually work out maybe even the age of the painting, or even, if we are restoring it, we're trying to use the correct the correct materials so it's not obvious. Obviously you wouldn't use a completely different paint, otherwise it look obvious, wouldn't it? So there's loads of different uses for gas chromatography. Okay, so we're going to look at something called high performance liquid chromatography, or HPLC. Now, HPLC is used where it may not be suitable to use gas chromatography, which is GC. So this could be, for example, a sample which has a really high boiling point or decomposes in heat. So, for example, if it's got a really high boiling point, it can't actually be carried through the GC machine. Also, if it decomposes in heat, because remember in gas chromatography we have an oven in there, if that decomposes, that's going to be no good, because we'd want to know what our sample is. And if it's all broken up into different substances, then that isn't any good. So there is a solution. So we use something called HPLC to do this. So we have the phases, obviously the mobile and the stationary. You'll notice in chromatography you always have a mobile and a stationary phase. So the stationary phase is solid, small or small solid particles. So this could be silica and hydrocarbons, and they're in a column. And the mobile phase is a polar liquid, and so this is things like methanol and water mix. So this is the mobile phase. These are the different phases that we're going to use in this type of instrument. And so the mechanics are that the HPLC solvent is pressurized, and we use that in a pump. So we've got a HPLC pump here, and the solvent is pressurized, and to which the sample under test is added. Okay, so this is it here. So a sample is added into the injector and is added and pushed through a column. So here's our HPLC column from our sample. So we're using pressure here, and we're using polar solvents. So you can see we're not using heat. So this is ideal for things like things which decompose in heat, because we're not using any. But also the boiling point, we're using pressure instead to actually turn it into the phase that we need, so we can identify it. So each substance, just like with GC, takes different amount of time to travel through the column and reach the detector. And so this is because some, again, for the same reason, some parts will spend more time in the stationary phase, some will spend more time in the mobile phase. And if you spend more time in the mobile phase, that's going to come out much quicker out of the machine, and so therefore the retention time is going to be lower. It's not retained in the machine as long. Whereas obviously if it's stuck on the stationary phase for longer, it's going to take longer to come through. And the stationary phase, the retention time will be longer, will be higher, so it'll take longer to come through. Okay, so after the sample leaves the column, it's now separated and entered the detector part, as we can see here. So here's the detector section. And so what happens is UV light is shone at the sample, and the absorptivity is measured here. Okay, so you measure how readily, basically it's a bit like colorimetry when we looked at as a method for measuring rates of reaction. You can use a colorimeter and it measures absorptivity, so if you remember that. This one is using a similar principle, but we're measuring absorptivity, and this information of absorptivity is actually pushed into the display screen here, as you can see. And basically these peaks here is the level of absorptivity, which is then relayed into this chromatogram. And each peak again represents a different substance. Each one has a different retention time, so it's exactly the same as your GC spectrum. And obviously we can then take that information and we can compare it with a known library of resources, and that will help us to identify the substances in our mixture. Okay, so gas chromatography mass spectrometry, so GCMS. So what we can actually do is we can combine gas chromatography or HPLC, so we can take either of them, and we can connect it with a mass spectrometer, and we can actually help to identify mixtures in a substance. Okay, so the mixture of substances, so the substance in the mixture, should I say. So it works fairly straightforward. So mass spectrometry is actually better used its use is much better at identifying compounds via their mass to charge ratio, but analysing a mixture of compounds is going to be very confusing, of course. If you put in 3 or 4 compounds in a mixture and put it through a mass spectrometer, you're going to get peaks everywhere because it wouldn't have a clue what is what. Remember, it's just measuring mass. So what we can do is we can use a separating technique such as GC or HPLC. And we can use that to separate it first, which we're going to do, because this isn't actually very good. Both of the methods are not good at identifying what compounds you have in your sample. Okay, it's mainly used to separate the substances out. Yes, we can compare it against a known library of resources, but what happens if you've got a chemical in there that it hasn't already been recorded somewhere? So your mass spectrometer is a better use for that. So if we combine these two together, we get the benefits of separating a mixture first into its individual substances, and then we can analyze each of them substances separately using a mass spectrometer. So it's a very powerful tool by combining the benefits of both to try and get what we want out of it. And so basically the separated compounds run through the MS machine. That produces a spectrum to identify each substance. So that's what we looked at right at the start of the video when we looked at the mass spectrometer. And so the mixture of substances, these are fed through the gas chromatography or HPLC machine, and this separates them out. However, instead of detecting it, obviously it feeds it straight into the mass spectrometer. So they're literally connected to each other. And then the substances can then be positively identified as the mass spectra produced can be compared with a library of known stored spectra on the computer. So this makes it a really efficient process. So actually the user may not even need to actually analyze the spectra. It literally just goes through, and the computer, if it recognizes the spectra that you've just done against a library of known ones, then that means it's much, much easier to do, isn't it? Okay, so this is going to look at the final section. The final section of this video is looking at combined techniques. We're taking all of them techniques that we've just seen there, and we're going to put it all together and actually get some use out of it. And they will be expecting you to be able to do this, of course, in the exam. Okay, so obviously chemists use a variety of different techniques to identify an unknown substance that we're looking for. And obviously the skill is putting all of this together using all the different bits of information that we've got from each spectra to try and identify a molecule. Okay, so this is what we're going to do here. So we've got 3 spectra of an unknown organic compound. We're not even going to say what that compound is in terms of its formula. So we've just been given a proton NMR spectrum, an infrared spectrum, and a mass spectrometry spectrum as well, so an SMS spectrum. So we're going to use all these 3 to try and identify an unknown compound. And we're going to go through them one by one, if I can get my words out. Okay, so we're going to look at the MS spectrum first. And so this is of our unknown compounds. So remember, it shows fragments of different of the compound that we're testing. So the molecule is fragmented or broken up into different parts. So we can tell straight away, remember, this is our M plus peak. So we have a peak at 58, and so we know that the molecular mass of our substance is 58 straight away. So that's what we're looking at there. We also have a fragment peak at 29. Okay, so this could be due to the CHO or C2H5. It could be either one of them. So if we add that up to 29, both of them fragments add up to 29. So that could be a classic sign. It could be one of them. So we can see from this, we can deduce that our mystery molecule has a molecular mass of 58 and may have a CHO group in it. Okay, so it may have something like that in there. So may not, but it gives us something to hook onto at least. But we need a lot more information to actually confirm what this molecule is going to be. Okay, so let's look at our infrared spectrum now. So we've got a little bit of information from the mass spec. So infrared spectrum. We have a peak at 1,750 centimetre or per centimetre, and this is likely to be caused by a CO. Now you'll have a data sheet with all the spectral peaks on for infrared, so you don't need to worry about that. So it could be because of a CO, and so from this we can deduce that we either have an aldehyde, a ketone, an ester, an acid chloride, or an acid anhydride. So we haven't really narrowed it down, but at least we know there's a functional group in there that could be one of them. Now, it can't be a carboxylic acid though, because the peak doesn't sit between 2,500 and 3,000, which is exactly where we'd expect to see a carboxylic acid peak. And it can't be an amide, as we'd see, as there's no peak between 3,300 and 3,500. So it can't be either of them. So we've narrowed it down a little bit, but not a dramatic amount. And like I say, we need more information to confirm what our molecule is, but we know a little bit more about it. Okay, so let's look at our proton NMR spectrum, and we're going to use this again to try and find out unknown compounds. So let's see what we've got. 3 different hydrogen environments, so we know that's the structure of this. And so we know we've got a peak at 9.5, and this is due to a CHO group, so that's good because we identified that as a possibility for mass spectrometry. There's also peaks due to CHX group as well, and so these are confirmed via infrared, so we know we have CH groups in there definitely because the infrared spectrum shown us that. So the peak at 1 which is this peak here, this one, okay, so this has an integration of 3, which suggests a CH3, and there's a triplet, which means it's adjacent to a carbon with 2 hydrogens on it. Okay, so we can see it's got 3 hydrogens on, and it's next door to a carbon with 2 hydrogens. So that could be a CH2, CH3, perhaps. Okay, so the integration peak at 2.5, which is this peak here. Okay, so that has an integration of 2, so that suggests it's CH2, and it's a pentet, which means it's adjacent to carbons with 4 hydrogens. Okay, so that's very, very important. And so this is likely to be near a CH3 and the CHO group identified at 9.5, okay, which itself is a triplet. So that one at 9.5 is a triplet. So this is showing it's possibly bonded to a CH2 group. Okay, so we've got a lot of information there from NMR. So the skill is to take all that bits of information there, and we're going to summarize it here, and being able to summarize, put it all together, and actually work out our mystery substance. So let's have a look. So the mass spectrometer, remember, told us that our substance must have a molecular mass of 58. Okay, that's the first bit. And our infrared spectrum confirms that there is actually a C double bond O group in there, so there's definitely that in there. However, there wasn't any other peaks to suggest any other functional group. Okay, so the NMR machine also confirms the C double bond O group, so this must be part, and that was, according to the NMR machine, that was an aldehyde group. Okay, so we know it's an aldehyde. And so the NMR machine also confirms that we have a CH2 and CH3 group, okay, which when supported with the mass spectra information, that the molecule had a mass of 58, we can actually start to build our molecule together. So let's have a look. So this is it here, so it's propanal. So you can see we have, this has got the mass of 58. We do have our carbonyl group there, because confirmed in the infrared. And also, if you look at our structure, we have a singlet, okay, that's bonded to our aldehyde group, which is fine, because that's what we've actually that's what we deduced from that. So if I just go back, there we are. Okay, so it won't be a singlet, will it? So it'll be a triplet because it's bonded to a carbon. So if I just go back, there we are. That's me not concentrating. So this is next door to, this is bonded to a carbon, which is bonded to 2 other hydrogens. So that would be a triplet peak, of course. It's obviously bonded to a carbonyl group, which shifted it over to the 9.5. This carbon here has got integration of 2, but is bonded to 3 hydrogens here, and also to this side, we've got one here. So it's got 4 hydrogens. Okay, so that fits. And obviously this one is an integration of 3 and is showing a triplet setup because we've got 2 hydrogens next door. So all that fits. Okay, so it's all about just trying to piece it together, get your evidence together, and just confirm and just draw a structure and see if it fits. That's the key thing, I think. Okay, and that's it. So that's the end of the video on modern analytical techniques 2. So you can see there's a lot of information in there. The key thing with NMR is just practice. Practice, practice, practice. Okay. There is a full range. This is the last video for year 2, but there's a full range of year 1 and year 2 videos specifically designed for EDEXCEL on Allery Chemistry YouTube channel, and they're all for free. There's whiteboard tutorials on there, and there's also exam practice, exam technique videos on there as well. They're all very comprehensive, all for free. All I ask is you hit the subscribe button just to show your support, and that would be absolutely fantastic. You can also purchase these as well. Like I say, great for revision. Just click on the link in the description box. But that is it. Okay, bye-bye.